So hello to everybody. Thank you, the organizers, for this opportunity to present my speech. And actually, it's about the quantum key distributions and 5G networks. And as the topic is quite hot, and actually I'm allowed to speak about 40 minutes maybe, so I decided to make a bit broader overview of the quantum electronics and start for some political, economical, technological context. And now there are quite many initiatives for European Commissions about the digital single market that also comprises the development of 5G networks and quantum flagship. And the so-called Quantum 2.0 revolution is ongoing. And to speak a bit also about the differences between the classical informatics and qubits and entanglement, and three main applications like quantum computation, quantum telecommunication, quantum sensing. And actually there are also some applications beyond this. So just maybe to understand how far or how close are to this topic, maybe could you tell, so are there any in the audience familiar with the quantum electronics or quantum computations, or maybe work on this region? So, not so much. You? Okay, great. Great. So actually, just tell me, you can stop me and ask the questions if the topic is material is too boring or too complicated. So, but I try to avoid difficult maths and talk more maybe about the applications and about the situation. So why 5G and why quantum electronics or quantum telecommunications? So the market analysts predict that there will be growth about maybe 400 times in the coming 10 years until 2028, with the annual growth rate something like 80% per year. And actually, if you see, so the situation is that the main growth is foreseen in the East Asia and North America. And actually, Europe is not so well in this situation, and European Commission has such an initiative called Digital Single Market that comprises these two topics, actually the development of 5G networks and quantum flagship. So that's more about the public services and economy and society, maximizing the growth potential of digital economy, development of supercomputers, artificial intelligence, blockchains, digital life like e-government, electronic identification, digital culture, smart mobility, and so on. And actually, if you look at the development of 5G networks, there will be something like three main topics. That's enhanced mobile broadband, ultra-reliable low-latency communications, that's more for autonomous vehicle, and of course, the massive machine-type communication, that's more about the Internet of Things. And such networks are already deployed, not only Europe, but other parts in the world, and it is planned that by 2020 there will be fully commercially available 5G networks in Europe. So what's more interesting, that 5G networks could integrate different type of networks. And actually, of course, the existing 4G infrastructure will be used, but there will be more enhanced connectivity between the cells. It will be much more broadband. And also such a different kind of connectivity, like a satellite, could be also integrated in this network, because there will be separate planes, like a user plane and control plane. And if we look at the development of the quantum technologies, so there are also massive investment into this topic. And actually, it's first in the United States, but China is also maybe at the second place. And now there are many investments done both by the national governments, but also by the European Commission, also in Europe. And there are quite many calls now. Some of projects are already running, so they have been announced in 2017. Now we have the second bunch of 2019. And full implementation of the first quantum communication infrastructure is planned by 2021. So just recently, just this month in June, on the 13th of June, so-called Quantum Declaration was signed in Bucharest, because Romania is now leading the European Parliament. And 6 states like Belgium, Germany, Italy, Luxembourg, Malta, Netherlands, and Spain have planned to develop these networks, and within the next 12 months. 4 topics are addressed in this quantum flagship project. That's quantum communication, quantum computation, and simulation. That may be more similar, but computation is more about the development of the hardware, simulation is more development of the software, and sensing and metrology. What's about the technology, and why it's important, and why these technologies like quantum came also not from the market, but also from the technological side? Actually, probably all of you know about this Moore law, that the density of the integrated circuits doubles every 2 years, and actually now we have reached such dimensions like 13 nanometers, 7 nanometers, 5 nanometers, and if you remember how much is the size of an atom, it's actually about maybe 4 or 5 angstroms, that's 0.1 of the nanometer. That means that we're starting to work at the level of maybe 10 atoms. And if you look at this graph, so probably we're coming to an end. And we have to try to work with not only with the material, but the single atoms, or maybe even less parts of these atoms. And also, there is such a famous relation that's called Abbe relation, that we reach also diffraction limit of the resolution. That means if the wavelength, it's comparable actually to the dimension we work, and we would like to work at such a level, and for example make a lithography. Of course, now it is, for example, electron lithography is made, but for the inspection it would be good to make also some radiative inspection. I mean by means of the taking the images. That means that we need also such sources. So that's actually soft X-ray or deep ultraviolet. And there's also another one, Moore's law, called Moore's law for the light, and it was presented just recently by Nobel Prize winner Gerard Mourou. And actually, if developing the short wavelength sources, we need more energy. And now we are somewhere, at the position when such centers like extreme light infrastructure are opened in Europe, in Czech and Hungary, in Romania, and actually we can reach already the wavelengths that are in the range of 1 nanometer or even less. So they are already calculated in kilo electron volts or even mega electron volts. But actually these installations are quite big. They are also, that could be free electron lasers that can occupy even several hundred meters, or such powerful laser installations that also take almost the whole building if you would like to reach such energies. And of course we need also different element bases and different spectrum, because to develop the high-speed communications we need more bandwidth and new, not only electronics but also photonics. And for the closer distances, so the lasers that are already used are mostly implemented, but they are more for the short-range communications, and for the long-distance communications you need new materials, new lasers that work at the standard telecom ranges, where the attenuation is less, and you can cover higher distances and also have the minimum of attenuation in this region. And if you take a look what are the applications and what are wavelengths used, so actually for the trunk connections, like long haul, like data centers interconnectivity, like the feeds to the 5G access network basis, so this standard telecom range is used, and also the technology like indium phosphide is coming. And for the automotive, for the lidars, it of course could be also visual range used. For the gas sensor, it comes into an infrared region, and for the analysis, for the sensing, actually depends what the absorption wavelengths are needed. It could be infrared range. What's about the quantum 2.0 revolution? What's the difference? Actually, we are using the quantum devices for quite a long time, but quantum 1.0, it's more about the collective management of the system. And actually there are many applications like lasers, like magnetic resonance imaging, like actually GPS technology that it's used in the smartphones and the cars. And just to remember that, for example, if these corrections of general relativity and they have been not applied, so we would have quite high errors. And because of the relative motion of the satellites, we have something like 7 microseconds a day, and because of the gravity and the difference of the gravity, the satellites are moving and their objects located, we have even more, 45 microseconds a day. And if these errors would be accumulated, so we would have something like 10 kilometers a day, so actually we couldn't use. So this theory works, and we have to take care about it. So if you talk about quantum 2.0 revolution, so we talk already about the nanotechnology and about the managing of the single atom, about the quantum computers, about the quantum information and quantum sensing. What's about the quantum? Probably not all of you are very familiar with the theory of quantum mechanics. It's actually, I'm also not a theoretician, but let's imagine that the particle is actually the wave. And now the people working at the cosmology, they even agree that we have only the fields in the universe. We do not have even the particles as such. And actually, when we talk about the quantums, we have to imagine that always we deal with the waves. And they can interfere, they can be related on each other. And this assumption should help to understand also like a quantum devices work. So these waves can go all the possible ways. And Richard Feynman has also proved this. If you have some source and a detector, so actually you have to take care about all the possible paths. And if we have this light or this photon going from one source to detector, so actually we have all the integral of all possible ways. And there is another one very interesting and even strange phenomena. It's called entanglement. But actually you can find that people speak something like about the Schrödinger cat, that it could be in the box, and at the same time it could be alive and dead. But I believe it's also not the conclusion for some theories like quantum mechanics. It's more about the nature itself. And actually we just have a state that is distributed between two states, and they depend on each another. So actually they have correlations. And if you measure one state and the states are entangled, so we have correlations and we can predict what is happening on the other side. There's also one of the famous so-called Heisenberg uncertainty principle, and it's very about the basics about the universe, but actually you can find such examples also in nowadays life. And just if you have to try to measure two values, like for example in the radar, the time and the frequency, so you cannot do this at the same precision at the same time. So actually, if you need very good resolution of the distance, and you send very short signals, actually, and you do Fourier transformation, so we have like a broad frequency range. So it's difficult to have the precision in the distance and in the velocity at the same time. Actually, if you, for example, try to listen to the sound waves and you have just a very short click, so it would be very difficult to distinguish what's actually the pitch or the frequency. And you need much more longer signal to recognize what's actually the frequency. The same is actually also about the atoms. And actually, it's really difficult to measure at the same time the velocity or the momentum and the position. And actually it's quite similar like you do also like measuring the Doppler correction. Some maybe more formal things, and they are not so much maybe to start understanding and start engineering, but they are really very important. So something like that mass independent on the velocity, something like photon is a quantum, and so this it's Heisenberg identity principle, and the particle could have also the wavelength. It's called the Compton wavelengths distribution, like fermions, what's actually mostly the electrons, could be some other like muons or others. Bosons is for the force particle, field particles, so they have different distributions. And as I told also this entanglement, so-called Einstein called it spooky action at a distance. I have written even the paper that it's impossible, but all the experiments after that have proved that actually it works. And so actually this entanglement is even more important than other properties for the quantum computation and quantum sensing. Maybe I can just skip it because just this formalism of the waves of quantum mechanics, but even if you work or will work on it, it's not a miracle. You have just to understand what's going about. So actually there are several postulates of quantum mechanics. First one, it's about the particles or the photons are the waves, and they're going to all possible paths. So if you're measuring, so they talk about some operators that you will get the values during the measurement, but actually during the measuring you are also destroying the state, and they talk about the conditions that the wave function is collapsing, and the expectation value, it's written that measurable property should be Hermitian, but actually the meaning of it that the physical expectation of physical value should be real, and the variables can be quantized, and you can calculate also the probability of this particle be in some particular state, and this normalized all the states to the one. And actually the evolution of the state is described by the time-dependent Schrödinger equation. If taken also very shortly how the measurement is done, so actually if you have these waves, so you have to do a kind of projection. For example, if you can project into the vertical or horizontal projection, so actually you are measuring the distribution, how much of the time the vector will be in vertical or horizontal position. And actually that's also the meaning of the qubit. So it can be not only in the position 0 or 1, it can actually in the superposition, and you have all the possible states that are in between. So if you entangle two qubits, or you have combination of two states, two qubit states, you get this entangled qubits, and we talk about a correlation. So if there is a good correlation, so they are fully correlated, so you have corresponding measurements, and you get the same one picture. There could be anti-correlation, that you, when measuring, there will be no correlated states. It could be something in between. And these states, it's normally could draw as a called Bloch sphere, where you have this vector. It could be between 1 and -1. It's actually about the state. For example, it's called 0 and 1, but actually it's just -1 and 1. And there are other two coordinates that are described like a phase, and actually this vector is moving on this sphere. And what is very important, and both for the quantum computations and quantum sensing, that if you try to calculate how many complex numbers are required to describe the system of n components, so for the classical bits you need just the n classical numbers, but for the qubits in the quantum physics you need 2 at the power n-1 complex number. And if this entanglement number is increased and you have so-called multipartite entanglement, with many particles in the system, you can get very quickly to the huge numbers. And actually that's the power, and that's the main difference of the of the classical computation and the quantum computation. So you can do so many operations at the same time, and it's called like a quantum supremacy. That means that you can create a kind of artificial intellect that probably could be even bigger than the human brain. And concluding about this theory, so these correlations can be measured, and they are checked at so-called violation of CHSH inequality. That's according to the first letters of these scientists, and that's about the conditional probability. Actually, if you have two independent states, and of course the highest probability to be in one of the other state, and sum of it, so it could be not more than 2. But if you're measuring this correlated state, you can get the correlation more than 2. And actually, this violation, it's a kind of proof that the states are correlated and they are in quantum correlation. It's actually this number is bigger in quantum world. It will be something like 2.8 instead of being 2, just 1 plus 1, like it's a possibility to be in some specific state. Okay, so let's come back maybe to some practical implementation, and I will make a short review about what is done in the quantum computation, quantum telecommunication, and also quantum sensing. So how the qubits are built? There are different technologies, and the qubits could be realized on the superconducting loops. So actually they work at millikelvin range. They could be organized something like called trapetines, the quantum dots. There are something like topological qubits, something like entanglement between different paths in semiconductor. They could be realized on nitrogen vacancies on the diamond, and there's called such like a spin photonics, like you can control the light with changing the magnetic field. And there are some new developments and photonic integrated circuits that so-called qubits on the linear optics. They work on so-called Hongo-Mandel effects. It sounds maybe a bit strange, but it's just a splitter, 50 to 50. And if you have two indistinguishable single photon source that enter this splitter, so you can have these 4 combinations, like on the left side, on the right side, on the both sides. But just because they are in opposite phase, so these two states canceling each other, and at the end you have just these 2 entangled states. And it's quite simple because you do not need any nonlinear elements, and actually there are some predictions that specifically this platform could be used for the reaching high entangled states, because for the future quantum computers we need something like 1,000 or several thousand of entanglement states, and actually splitting such a way you can do so many entangled states. And if you compare how much of entangled states they are reached now, so they are not so many, and of course there are problems also with the sources itself, and different sources are used. So mainly we talk about maybe 3 types of the sources. There could be actually not a single photon source, but something like a weakly coherent photon source. That means that it's attenuated at such a situation that it has the mean value 0.1. That means that it has probability that single photon will be emitted something like 9%, a probability of multi-photon states something like 1%, and there will be no photon 90%. But if you're attenuating just a simple laser, you can start working and do different quantum circuits. And there are so-called heralded photon sources that work mostly on nonlinear optics. And these nonlinear optics, that means that the photons generated are in pairs. And actually, if you measure one photon, so you can be quite sure what is the other one. And they are deterministic single photon sources that mostly now they are on the research state. Some of them actually are already try to produce some real qubit circuits. and mostly they are realized on the quantum dots, color centers, or carbon nanotubes. What we need for the quantum computing? Actually, we need these qubit states. We need actually well-defined, well-isolated, and it's really not so simple. The first quantum computers, all of them are working in the very low temperatures, like less than 1 Kelvin, and we need quite long coherence time, and also I need these quantum gates, like also in the similar computing, to perform the measurements and perform the computations. And the latest achievements that such a actually big companies like IBM, Google, so they are for the moment at the stage that the ion technology, they are about the 20 entangled photons, qubits, at the superconducting qubits technology, they are about 50, 70, and these linear photon qubits, they are realized for the moment about 10. So actually, the people are working on that, but for the moment, actually, unfortunately, they didn't have reached such a situation that so quantum computer could be better than the classical computer. But I believe it will be. It will be quite close future. And if we also compare what is the level, let's say, of the development of the quantum internet stages. So the first one level would be just to preparing and measuring this quantum state. The second one would be to work with the entanglement states. Then, of course, to transfer, for the bigger distances, we need a quantum memory, and it's also quite sophisticated, because if you do just the measurement, the simple measurement, just destroying the states, and to have the full scale quantum computing, you need the synchronization, distributed quantum computation, and other things. Let's maybe switch to the quantum communications. So why it is important? Because if you have these quantum computers and you have such a lot of information that could be processed at the same time, so actually all the classical encryption schemes, like for example RSA algorithm based on the factorization of 2 primes, could be broken, and you need something else. And actually that could be, for example, the measurement of quantum states that actually are intrinsically secure. And if you have these entangled quantum states, so they are even more better, because the transmission of the entangled quantum state, that means that it is also so-called source independent. Because if you have just the first case, as I mentioned, with this weak coherent source, you can have some attacks, and there are also new topics, so-called quantum hacking. So actually, there could be something like quantum photon splitting attacks, or something like blinding of the detector, and there are things that you have also take care. But for the entangled photon source, so actually it's sufficient to measure the correlation at the end of the transmission, and actually you do not need any other measures to define if the signal was attacked or not. And of course you can build also very reliable quantum key generators that could work and provide a high type of security. How these keys are distributed? There are actually several technologies. This first one is now realized both by the satellites, both by the fibers, and actually it's also the part of this Quantera project. So there's one lack, but also one advantage, that for this case you need so-called trusted repeater or trusted node. Because you share the key with one station. That's example with the satellite, but it works also similarly also on the fiber. And then you share the key with the other own station. Then the satellite publicly announces the both keys, the parity of both keys, and you can use it for the encryption. But actually, the satellite itself, it keeps the all keys, and that means that the satellite itself has to be trusted. So somebody hacks the satellite, so it will be not more secure. And there are different schemes like distribution from the satellite to the ground station, from the ground station to the satellite, sharing this quantum keys between two stations, between the entangled satellites. And of course it would be much more interesting to have the entangled based quantum key distribution, because in that case, as I mentioned it, the no trust node is required. The realization, there's one example, by the way. So the Chinese colleagues have done much more work than the Europe. And something, of course, is done in the United States, but it's also part of this work is classified and not so much also public data available. But they are just two schemes how the coherent weak single source is realized, and also like entangled photon source based on the nonlinear optics is realized. Maybe I will not go into the details, but as I mentioned, their main difference are that the first one requires the trusted node on the satellite, and the second one, the sufficient is just to measure the coloration between the entangled photons. And this will show also one of the sources that are developed here in the Lithuania, in our Center of Physics and Technological Sciences. And actually, it's the differences from the Chinese one development, that it's much more integrated and is based on the fiber laser. The fiber laser itself also doesn't have such a so-called saturable absorber that allows to form the short pulses. It actually works on the cell phase modulation. That's more reliable. And the source itself, it's based on the nonlinear four-wave mixing, but everything is realized on the fibers. And actually we have something like three outputs. One for the classical communication, because if you would like to establish the satellite link between the satellite and Earth, you need much more powerful beam, and you have to tune the parabolic dishes, parabolic telescopes. And actually the another one is used for the modulating the polarization and also splitting into the two entangled photons. And actually you have additionally this polarizing splitter, and it goes one way into Sanyard loop, other way. So you have this uncertainty, and you generate vertical or horizontal polarized entangled photons that could be then split by the frequencies and sent to the different users. So how it looks like, so actually that's the image of the mysterious photon source that was tested in the real life a couple of years ago by China, and that's the size of the integrated fiber source that's developed now in our center. And it could fit even in a small satellite platform like 6-unit CubeSat. If we take a care about the attenuation, it's also quite important. And some people say that entanglement could take about the Alpha Centauri and another end of the universe. But actually it's not true, and the Chinese experimental data have proved it. So you have to take care about attenuation, because it will decohere the signal. That means that you will lose the photons. And actually the real situation, what could be used, anyway, you need something like maybe at least 20 centimeter parabolic telescope at the transceiver side, and something like 30 or maybe 1 meter telescope at the receiver side. And then you can make this reception of the optical quantum keys. And there are some real data. So actually the rates are quite small for the moment, but anyway the satellite itself is providing much less attenuation compared to the fibers. So this red line is the attenuation of the fibers, and it raises exponentially. And actually for the moment, without the quantum memory, or so-called quantum state swapping, you can go just to approximately maybe 100, maybe 200 kilometers, and that's it. With the satellite, you can go up to maybe 1,400 kilometers. And just if you had just the single link, so this so-called prepare and measure protocol, so the real rates of the quantum key distribution, they have reached something like half megahertz, so 440 kilobits. And after some improvement of the privacy, so the final key rate was just 40 kilobits. But if you use this entanglement, so actually you have to go twice the way. And the distance is about more than 2,000 kilometers. And actually the total attenuation is up to 60 or 70 dBs. And actually they have got the signal, but unfortunately it was really quite low. So actually they have the clock rate about 5 megahertz, and they have just 1 to 3 bits per second left. And actually the good news that the photons are entangled and they're really secure, but the rate is really small. And actually to use it, actually we need to have a kind of gigahertz rate entangled photon sources that for the moment are not so much available in the market, but the people are working on it. So then we can come to some rates that are useful in the real life for the distribution of these quantum keys. There's some scheme proposed by the Chinese, but the work is actually done also in the United States and Europe, Singapore, Canada. And the plan is to have something like combined network. So I mean to have metro network based on fibers, and this specifically this infrastructure actually is built now in Europe. And there is also agreement in Europe signed between European Commission and European Space Agency to provide also the satellite segment. And actually it would allow also the key distribution, not also across the country, but also the longest distance what this Chinese experiment was. It's actually between the China, I believe it was Shanghai and Vienna. So it's actually intercontinental distribution of quantum keys. If you have to go more, you need quantum memory. And as I told, it's not so simple, because you can not just measure, because that case you will just destroy the state, but you can swap. And these quantum memories are based on so-called spin photonics, when you can encode this quantum state into the magnetic state, spin state, and then to radiate, to transmit another one state. But this phenomenon is called entanglement swapping. In such a way, if you have sufficient time that this intermediate state can live, you can use it as a quantum memory, and it could be used also for the quantum computing. But these things are mostly at the research level for the moment. And China has even more ambitious task. They are going now, probably you know, that they landed on the dark side of the moon. And they have also the telecommunication satellite in the Lagrange point 5. So the ambition is to transmit these quantum keys with the entanglement memory swapping on the Lagrange point 5 between the moon and the Earth. So the world is moving. Now, a couple of words about the quantum sensing, and I will finalize my talk. So what's about the quantum sensing? So why it's better and why it's important? Of course, if you deal with a single atom, so you need much more energy, so much less energy to change the state, and actually that means that the sensitivity of such a sensor it's really high. That's, for example, these quantum sensors are used for measurement of the magnetic field, and it could be used for the improvement, for example, of the magnetic resonance imaging. They're used in atomic clocks, in synchronization, and for example, if such a devices would be available just like a circuits, and as an example that there's such a high precision that you could measure with this atomic clock the difference in the gravitational 1 centimeter of gravitational shift, just if you lift the sensor, so that means that it measures the gravity, the change of the gravity of the Earth. And the another thing, if you have disentanglement, so you can reduce the noise or increase the resolution. And if you have n of entanglement states, so actually you can go so-called super resolution. So that means that you can increase the resolution of the imaging or some other management, and that's how the entanglement can help. So quantum informatics, it's also very important for the life sciences, and not only for the simulation, but also for the real biological systems, starting from the photosynthesis, that how the light, the energy of the light is converted into the chemical bond, chemical energy by the transmission of the protons. There are some research made on how the birds recognize the magnetic field, and there's proposed such a theory that actually it could be also something like generation of the triplets of radicals by the sunlight in the eye of the bird, and these states becoming entangled between the nuclear spin and electron spin of these states, and actually the bird can some way see the magnetic field on his eye. And there are also some assumptions that even the human brain could work in a kind of entangled manner, because for the moment it's much more effective than the classical computers. So maybe. So this is the image how the brain memory looks like. So probably it's a bit similar to the quantum computer of the IBM or Google. What's about what's beyond? So actually, the theory is developing, and we have these nice scientists that worked in the theoretical physics starting somewhere from the last 19th century, the 30th year of the 20th century, and now the last, maybe most important discoveries was made like a Higgs field that was predicted in 1964 and just confirmed experimental at CERN 2012. And actually we move further, so that we have not only atoms, we have a bunch of different elementary particles, and this zoo is growing. So actually the last one is the Higgs, Higgs boson that actually proved that it can provide mass. That's what I was told, that actually all the reality what we see is actually the fields, just their specific fields that could provide the mass. And there are many theories developed that some way you can go unite these forces. So actually at the same level there's also such an energies reached that electromagnetic force and weak force are already combined. There are theories that you can go up to the combination, uniting of the gravitational force, strong nuclear force, and to come something like the theory of everything. But actually the energies are really high. So we need additional, 20 maybe orders of magnitude to reach such levels. But why not? Why not? Maybe the cosmological things are also looked at that, and there are theories that even such things like a so-called Great Big Bang, so the beginning of the universe, and what we can see is also a kind of entanglement, and that means that they have this singularity, and maybe this is actually the picture of the black hole of the Milky Way of our universe that's got just recently. So maybe it's just the entrance into the another one universe by the type of entanglement, and you can travel to this wormhole. Okay, so finalizing my speech. So I talked about the development about the commercial 5G networks, and European Commission stating that will be deployed or the commercial by 2020. Quantum communication infrastructure will be deployed later by 2021. So we have now this quantum 2.0 revolution with the managing of the single atoms, and this entanglement helps a lot for the quantum computation, so they become much more powerful, and actually we have this exponential growth of the computational power, like 2 at the power of n minus 1. We have possibility to have very secure quantum communications and actually quantum random noise generators. And we have quantum sensors with ultimate precision, and the resolution could be improved by means of the entanglement, and there are many new quantum revolutions to come. So thank you very much.
Maybe we have questions from audience, please.
We know this term quantum computers for maybe several years, for many years. If really there exist already developed quantum computers, or are still they in development stage?
Actually, there are some I have shown in one of the slides. I'm not sure if I found it now, but actually they are on the level between maybe 10 and 70 qubits, and most of them are now in the superconducting technology. So that's what I meant. So they are about maybe 20 entangled ions technology, qubits that are developed entangled ions technology. About maybe the best achievement is 72 qubits in the superconducting technology and 10 entangled photons technology. Of course, there are already some software development, technology developed, but to have this advantage of the quantum computation, actually you need about thousands maybe of qubits. So that means that is a long way to go. And one of the ways is this linear optics. That actually is much more simple, and you can entangle more photons. If this technology will be successfully developed, because actually it's kind of photonic circuit, so probably you could have, I don't know, thousands of photonic entangled qubits in the circuit.
Thank you.
More questions? I have one question. When we replace this laptop with quantum computer, could you predict?
Good question. But who knows? Maybe, I don't know, in 10 years we'll have the result. If you follow this law, more laws so about the density, so maybe the density itself, but maybe the computational power will raise. So I'm optimistic. Maybe 10 years.
So 33rd conference will be held on
held on the quantum laptop. Yeah.
Okay. Ulrich, thank you for presentation. Now it's lunchtime. Lunch will be served next to building A, in A building, and we will meet you less than an hour. We have 1 hour for lunch.